And in this case, we add additional 2 transistors, so it becomes even larger. So then, people are interested in emerging technologies like RRAM. You have a question?
In the previous slide,
Yes.
each SRAM cell is storing 1 bit, right?
Each SRAM is storing 1 bit, yes.
So for the 5-bit configurable unit cell, where would the 5 bits? You would have 5 SRAM cells placed in parallel. Is that what it is?
Yes. Yes. So that's why people would be interested in the emerging technology, because you can have multi-level per cell. So you don't need 5 cells for 5 bits, right? You hope you can have 1 cell for 5 bits. So this is the hope. As we say here, possibly multi-bit per cell. Ideally, you want to have larger than this 100 megabytes on chip memories to store all the weights on chip. If you can do that, then you reduce off-chip memory access. Because as long as you go off-chip, you have to pay the additional energy. So the other advantage for the emerging technologies like RRAM is that this is non-volatile. So you can always do this dynamic power gating as we discussed before. You can turn off your chip and turn on your chip instantly, so you don't need to wait for your model to be loaded from somewhere. If you use TPU or use SRAM-based approach, then your network model must be stored somewhere, right? Because after power off, your data is gone. So then you have to load in your model from somewhere. Either you download from cloud, or you have a separate flash. You have to load in your model from somewhere. But if you store your model directly into this non-volatile memory, then you can power on your chip and do the inference right away. So those are the possible advantages. And in the recent years, there are many research work going on from different groups. And I just want to show the attention about the recent work, again from the NTHU group from Taiwan. So they implement this 1 megabit RRAM array for the neural network and achieve like 21 teraops per watt energy efficiency. So this is the principle for the RRAM-based design. Similar as SRAM, you can think that in a neural network, you map the input as voltage to the memory array. In this case, we simplify it to be like crossbar array. Of course, you can have 1 T, 1 R there. But your RRAM resistance, let's say conductance, is mapped as the weight. And then you have voltage in, and then conductance, you get current, and then you're going to sum up all the currents. Then this final current is proportional to your weight and the input multiplication results. So you can have this one. And again, you need ADC to quantize the current to digital value. So this is the same principle, but with different technology. In this case, you use the RRAM. And in our group, we recently did some design to implement this kind of 2T, 2R XNOR-RRAM bit cell design to implement the XNOR neural network. So what is XNOR-net? It's very simple. So in this case, everything is quantized to be +1, -1. So your weight, just the binary, +1, -1. Neuron, just +1 and -1. So when you have those two multiplication, so it becomes XNOR operation, because here, for example, input -1, weight -1, your output should be +1. And then, let's say this +1 times +1, you get +1. So essentially, it's like XNOR operation between your input and the weight. So we call it XNOR operation. And then this is XNOR-RRAM chip. So how we did this is to use 2T, 2R as 1 bit cell here. So 2 of 1 T, 1 R cell. And then the input turning on those two word lines, always complementary to each other. If the input is -1, then we have 0, here and 1 here. If input is positive 1, we are going to reverse the pattern, 1 here and 0 here. So this is a complementary input. And then the weight are stored in the resistance of the state cell. If rate is -1, then the top cell is high resistance state. The bottom cell is low resistance state. If weight is +1, then we reverse the data pattern. So the top is low resistance state, and bottom is high resistance state. So you can do this practice by yourself. You will find that only when the input is 1 and the cell conductance is in the low resistance state, you will have current through this branch to discharge your bitline. So you will see this only when the input is 1 and the cell is LRS, then you will have discharge current. So then this is essentially doing this XNOR computation for you using the bitline. Similar as the SRAM case, you can enable multiple rows in parallel and then count how many discharge current through multiple rows. And then the more discharging current, that means this weighted sum value is larger. So you, at the edge of the array, you still may need to use the ADC to quantize the output. So no matter SRAM or RRAM, so we need to do some modification for the peripheral circuits at the array level. So in the memory design, we have the decoder, right, to turn on one row at one time. But in this case, we do the computation. So we have to turn on multiple rows at one time. So you need to change the decoder to be a switch matrix to allow you simultaneously turn on multiple rows depending on the input vector. So this is the first modification you need to do from the peripheral circuits point of view here. And then the second one is we need to use ADC instead of 1 bit. So when I say multi-level sense-amp instead of one level, 1 bit sense-amp. Because in the memory application, you just need to determine 1 or 0. Here you need to look at what is the weighted sum value in the multiple bit precision. So depending on your ADC design, if your ADC reference is not linear, and then you need to use a lookup table to make it linear. So you need to have this conversion. And recently we did the tape out for this XNOR-RRAM chip, and with collaboration of my colleagues at Arizona State University. And the array, similar as what I described earlier, we have this 2T2R as 1 bit cell. And then at the edge of the array, we are going to have this pull-up PMOS transistor as a load. And then essentially, we are going to use voltage mode sensing to sense this node voltage depending on your input pattern and the weight pattern. And then this is essentially like a flash ADC. You have multiple voltage mode sense-amp as a comparator with different references. So we are going to compare this load voltage with different reference voltage, and then you can determine this load voltage is in between which and which reference. Then you can get the output. And if you simplify the circuit, then it will be something like this one. So this is a load, and then we have the PMOS as a pull-up, and then all the current. If, for example, here this one is input is 1, and this is in LRS, so this will discharge the current, okay, to the ground here. So this is going to discharge current. This one is also going to discharge current. So it's like there are many possible parallel branch to discharge that node. This is to discharge this node through those multiple branch. If the input is 1 and this this resistance is the no resistance state. If that condition happens, then you are going to discharge that node. Then the computation is essentially counting how many discharge paths available there. So then you are doing this annual computation depending on your input pattern, depending on the data you store there, how many of them are in the low resistance state. And not how many, let's say the matched. The input is 1 and then matched with the no resistance state. Then you have discharge. So then this node voltage can vary. So here is some measurement result on this node voltage depending on the bit count value. So how many of them discharge? Okay. So then you can vary this node voltage, and then you need a analog to digital converter. So you sense this node voltage in analog voltage, and then you convert to the digital output. So here we use 3-bit precision for the ADC conversion. So that means we have 7 references. You can have 8 level and 8 analog levels, and then we convert that to the digital output. 0 to 0 bit, 1 bit, and 2 bit. In total 3 bit. And this is a chip we designed. And here, this is the array. It's like 128 by 64 array size. And then this is the layout. So the array is pretty small, but the ADC here is pretty large. So this is the ADC. So this is the key design challenge we face. The ADC takes too much area. And even in this design, we shared ADC, 8 columns share one ADC. There are 8 columns here. So this is not ideal because the area of ADC is so large, so we have to share them across multiple columns. This will degrade the throughput, because ideally the principle of this analog computation is that we can get the output in parallel in one cycle. Because you share the ADC, then you need to use 8 cycles to read out all the outputs. So your throughput is divided by 8. This is due to the design challenges in the practical chip design. So this is a challenge we see. Nevertheless, we still perform okay in the metrics here. For example, the energy efficiency, we can achieve like 24 teraops per watt. If the input is 1 bit, weight is 1 bit, and the ADC output is 3 bit. So if you compare the prior work from National Tsinghua University from Taiwan, so their input like 1 bit, weight is actually 1.5 bit, with 3 level is between 1 bit and 2 bit, and output is 4 bit. So they can achieve like 53 teraops per watt, a little bit better, probably because of the lower technology load they use. So here is 90 nanometer CMOS. Another metric is the throughput. Okay, so one is energy efficiency, one is the throughput. Throughput, this design is better from the prior design, because prior design only, I think 8 rows or 9 rows are turned on simultaneously. This one will turn on 64 rows simultaneously. So then you can improve the throughput because you turn on more rows simultaneously. If you turn on less rows simultaneously, you need use more cycles to finish the computation. For example, first you turn on first 8 row, second cycle you turn on the 9th to the 16th row. So you need to use more cycles to finish the computation. That is your throughput. And in this case, the throughput is better because we fully turn on all the rows. So then the figure of merit is the EDP, energy delay per duct. Essentially is this. energy efficiency multiplied by the throughput. That will be the energy delay product. So if you do that, use those two numbers, you multiply them, and then in this our design, it will be like 3 times better than the prior work. We are a little bit worse in the energy efficiency, but better in the throughput. But overall, the energy delay product will still like 3 times better than the prior design. So this is the state of the art in terms of the RRAM design. I think in the community right now in the in this field. So the challenge here we see that is the degradation of the accuracy. Okay, this is generally true in this computing memory approach. In memory computing approach, when you use analog computation, you will face this challenge. So we run the neural network on this chip, and then the CIFAR10, which is this image recognition, the accuracy is only like 83% on the chip. But if you run this in software using your GPU, you can easily get 90%. So there are a few percent degradation from the chip compared to your software baseline. So why is that? Any idea?
For defractization.
Also, the input is 1 bit precision.
Input precision is no, but if you compare in the software, you can also do the quantization to 1 bit input and 2 bit weight. It's okay, you can do that. You can still get 89, close to 90% accuracy. So that's not a big problem. So the big challenge here is the process variation. Due to the analog computation, you add up the current. You are summing up the current in analog domain, and later you use ADC to convert that analog current to digital output. Because ADC will have the process variation. So let's say this column's ADC and the next column's ADC may have some offset. So every time you are not going to get the ideal output. So that contributes to your accuracy degradation. So this is a key challenge we face. Not we face, everybody doing this kind of research will face this challenge. So that's a trade-off between the energy efficiency and the accuracy of your network. So depending on your application, if you don't care about that a few percent drop accuracy, then you can use this one because it will greatly improve your efficiency and your improve your, if you use edge device, improve your battery lifetime. So what we have designed and taped out so far is just this one subarray, and in the chip, in the silicon. So in the either SRAM case or the RRAM case, it's just one subarray. But of course, the neural network can be very large, so we need to have this kind of hierarchy in the whole chip. So multiple subarray need to be grouped to be this one processing element, and multiple processing elements need to be grouped to be one tile, and then you have multiple tiles to run a very large neural network on this chip. So right now we are just at the very initial step in the silicon. But of course, we can do simulations for the whole architecture. That's no problem. So then just a few more words on to understand the convolution for the convolutional neural network. So here you have some input feature map, which is your input, and which has this dimension, H and W. And then your filter, which is a kernel of your convolution, which carry your weights, have this kind of dimension R and S. So we are doing the convolution between those two. What does that mean for convolution? Okay, convolution is the element-wise multiplication between the input and the weight. So what we are doing here by convolution means what? Here, the symbol for convolution is this cross. So we are going to basically have this window size equals to the filter size to your input feature map. Typically, input feature map can be large. Your kernel is typically small, like 3 by 3. So you only have 3 by 3 9 pixels here. So you are going to use the same window for your input feature, which, for example, the first layer can be your raw image. And then you have this window, and then you do element-wise multiplication. That means the first image, first pixel in this image is going to multiply by the filter value here, and then you get the multiplication results. And then you're going to get 9 results in this case, if it's 3 by 3. 9 dot product results, and then you're going to sum up that product to be one element in the output feature map. So you do the element-wise multiplication, and then you add those dot product results to be one output in the output feature map. So this is how you do the convolution, okay, for one input feature map and one filter. And this is typically seen in the image processing. For example, the filter in the first few layers can be this edge detection. So essentially, if you use this edge detection kernel, apply this kind of kernel to your input feature, you are going to see the edge of the images where the contrast changes. So this is the typical step, but this is just one input feature map and one filter. So the convolution neural network will have many of them. Okay. So what you will do here is you finish the first element here. You are going to slide the window to the next one, and then you are going to redo this computation, and then you get the second output element here. So you are going to scan over this input feature map using this filter window, and then you get the output feature map. This is just one filter and one input feature map. As we discussed, for convolution neural network, you will have many of them. Okay. For example, here you will have input feature map and the filter channel. Let's say C, number of C. You have many of them, many input channels. So then you are going to you will do this, let's say, a multiplication and then adding of all of those results to be the one element in the output feature map. You are going to sum up this kind of multiplication across multiple channels and then get one element in the output feature map. So this is what you are going to do. And then you may have different filters, okay? Maybe the first filter look at this kind of horizontal edge, the second filter look at the vertical edge. So you have many of them. If you have number of M filters, then you are going to generate number of M output feature map. So each of them is going to generate, let's say you do this multiplication and the summation, you get one element here. But you have M filters, then you need to repeat this computation and then get M output feature map. Okay, so you can see a lot of computation here. That's why this is very computation intensive operations. That's why you need those GPU or TPU or this in-memory computing to help you. And then you may have different input feature map. Okay, that means you are going to process multiple images. Then you are going to repeat this process and then generate this kind of multiple output feature map. So this is the eventual operation for you. So if you look at this, is your filter, okay, is a cube here, and you have multiple filter. That means a cube is three-dimensional thing, okay, and you have multiple of them. You add one more dimension. So essentially, your weight are stored in a four-dimensional tensor. So that's why Google is developing TPU to process this tensor. So you have this tensor, okay. So then the question is, when you map the four-dimensional stuff into a two-dimensional memory, how do you do that? Because eventually all those data need to be stored on memory. And typically, like SRAM was two-dimensional memory already. So you need to think about how to map